All right, so this is an example of a chi-squared goodness of fit situation, which is, I think, what we're going to be dealing with here when you're dealing with just a list of data. So the question that we're going to be working around here is, are the births of successful people uniformly distributed across the signs of the zodiac? When we're dealing with chi-square problems, we are dealing with counted data. And we are dealing with comparing what we observe with what we expect to get, which is a big part of inferential statistics. It's a big part of why we study statistics, comparing what we get with what we think we're going to get. And so this is going to be pretty much a crash course in this. This is going to kind of jump over a lot of things that you might otherwise have to address in an AP course, and things that you still might need to address. But there's a pretty easy workaround. Mathematically, the math isn't all that hard, but there's an easy way to deal with it in the calculator. I think it's easier to show you to go over that in person rather than try to do this. I don't have a very good, reliable emulator right now for the TI-80, or I would. So let's try to answer this question and see what we can do here. So we got to get some data here. So we've got the this table here represents the zodiac signs of 256 Fortune 400 executives. So this is the observed data. So anytime we're dealing with a goodness of fit test, or a chi-squared goodness of fit test, what we want to do is we have to write what we're doing as a series of two hypotheses. And again, I'm not entirely sure this is what you have to do, but it's kind of what I think would kind of be a baseline thing that you have to do. So the question is, are they uniformly distributed across the signs of the zodiac? Our null hypothesis is that they are. It's H sub O, and that's saying that yes, they are, and they are distributed, or uniformly distributed over the zodiac signs. The alternative, H sub A, the alternate hypothesis, is births are not uniformly distributed over zodiac signs. How these hypotheses work is, we assume the null hypothesis to be true unless what we see in our data and is different enough for us to confidently say that's more than just a little bit off, that's off by something more. For example, the easiest example I could give is, if you want to test the fairness of a coin, right? And you flip a coin 100 times. You wouldn't be concerned if you got 54 and 46 heads and tails, right? You should get 50-50 in theory, but you're not going to. 54 and 46 is close enough that's not going to be a concern. That's just sampling variation. If you got 80 and 20, that's more of a difference than we would be willing to accept as acceptable, I guess. So if we have enough information, we're going to work under the assumption that the null hypothesis is true unless we get some sort of indication that it's not, and then we're going to go with the alternate hypothesis. So what is that indication? What are we going to do? Well, we're going to take and use we're going to try to find how much, we want to quantify how much our observed values, which is what we see in our table here, differ from our predicted value. And that's the formula for the chi-squared distribution, is you take the observed, which is what we have here, minus the expected, take that difference, you square it, and you divide it by the expected for each of these. So in this particular problem here, we'd have to do this 12 times with these 12 different observed values, right? then we would, what this is telling us to do right here, as we know, is add them all up, right? So we do this part here for each of those, and then add them all up, and that is going to give us a number with which we can find some probability. And looking at them, you're saying, well, okay, they all seem pretty close, but what is the expected value? What would we expect? Well, if we are dealing with 256 executives, and there are 12 signs of the zodiac, if they were evenly distributed, if they were uniformly distributed, we would simply say, okay, well, the expected value, we would expect about 21.3 for each sign. When we're talking about expected and observed, expected can be decimals. Observed can't be. You're not going to observe a third of a Taurus or a third of a Scorpio. That doesn't make any sense. But we would expect, on average, there to be 21.3. Right? So if we took many, many samples of 256 and found the average number of any particular sign, we would expect it to be 21 and a third. Okay? So now we've got our observed, we've got our expected, and we want to we want to do all this with these numbers. And you only need two. It's kind of nice in that regard. You don't need a ton of numbers, and it's not super complex math by any means. But we have to do it for all of them. Now, what's nice about this is we don't have to show, if you were to do it out by hand, you would have to do it for all of them. So I did it for the first two here, and then the magic of the ... and I got to the end and then did the last one. And you notice here that 11, when we're dealing with chi-squared distributions, we have to, in addition to having the observed and the expected, we also have to know what are called the degrees of freedom. And those are just one less than the number of values. In this case, since there are 12 different signs, we would have our degrees of freedom would be 11, which is going to come in, which is definitely something you're going to need to know when you plug stuff into the calculator, right? So what our chi-squared value for this would be is 5.09. Now, okay, well, what does that tell us? Right. When we plug this into the calculator, and if you have a graphing calculator, if you have a Texas Instruments, graph TI-83 or 4, whatever, right? And we want to say, okay, so I want to figure out what's the likelihood that I get a chi-squared value, a chi-squared statistic that is greater than 5.09, right? And so just to jot these down, second, vars, there's a button vars kind of right next to the clear button. Right? So you go second vars, and that'll give us our distribution menu, and you go down to chi-squared CDF. Right? And when you get to the chi-squared CDF, what we're going to type in is 5.09, a really big upper boundary of 1,000, and then our degrees of freedom. Right? And when you type that in, that will give us our p-value. What this measures here, this 9.27, is giving us, that is the likelihood that we get a distribution as spread out as this one. Right? That will you know, if this is true, if births are uniformly distributed, how likely is it that we would get this distribution of with this much spread in these 12 signs of the zodiac? Really likely. Really likely. So what this says is this is a high p-value right here, 0.927, almost 93%. If your p-value is less than 5%, if this when you plug this in and you use your calculator to get that likelihood, right? If you get something that's less than 5%, that's where it's too different. That's where that distribution is too unlikely to be happening if these actually were uniformly distributed. If you've got a p-value of less than 0.05, then we'd go with the alternate hypothesis. We always have to accept one of these. So we're going to go with one or the other. And we're going to start with the assumption that the H sub O is true. And since when we plug all our data in here, and there's an even easier way to do this with two different lists, and we can do that in person. But what this is telling us here is this distribution is going to occur about 93% of the time when they're uniformly distributed. It's not all that unlikely that these things here. So that's enough for us to say our evidence supports the claim that, yeah, they're uniformly distributed. There doesn't seem to be any sort of indication that success favors a particular sign of the zodiac, right? And that's all based on a chi-squared distribution, where we are quantifying what we see, the observed, with what we expect, and running it through our calculator to get the likelihood that we get the distribution of observed values that we see. I hope that made that maybe a little bit clearer. We definitely can go over it more as if we need in person, where I can show you the graphing calculator, which makes all of this unnecessary. And if you don't have to do it, you don't, because it's kind of tedious. All right. Hope this helped. Let me know if you have any questions.